In this video, I want to talk about the residue theorem. The residue theorem is literally the result that we've been building towards all semester. It's going to encapsulate lots of things that we've talked about with integrals. So it's a generalization of the Cauchy integral formula. It's a generalization of the generalizations of the Cauchy integral formula. So if you remember, there were versions of the Cauchy integral formula with powers in the denominator. So we'll talk about how all that's related. And basically what the residue theorem tells us is that if you want to calculate the integral of a function over some region, all you really need to understand are what are happening at a few specific points, namely the singularities. So let's write down what the residue theorem is, and then in the next few videos, we'll talk about how to find residues, and then we'll kind of put everything together and do some examples. So first of all, the residue theorem says the following. So we're going to let f be a function that's holomorphic. So f is going to be holomorphic on some set. So on a region G, remember region means open and connected set, except at finitely many spots. So except at finitely many points. So except at finitely many points, let's call them Z1 to Zn. Okay, so G is holomorphic on a region G except at finitely many points. And then let's suppose that we have a curve gamma that has all the nice properties that we want. So suppose gamma, in G is closed, piecewise smooth, so all the hits. So closed, piecewise smooth. So closed, piecewise smooth, positively oriented. Simple and contractible. So remember that means that gamma contracts to a single point in G. Okay, so G is the entire region, including the points Z1 to Zn. So you can kind of just think of G as, this entire region and then all the points in between, even if f is not well behaved at specific points. We're still thinking of G as the whole set. This is a little bit of a departure than how we did this before, when we think of G as kind of all the red points except the black points. Here, G is all the red points, even though the function's not well behaved at the other points. So just a small subtle distinction there. So it's okay to talk about gamma being contractible in G, even though we have spots where the function might not be holomorphic. Anyways, and suppose one thing that I said that's kind of not explicitly stated, but possibly is understood, is suppose that these points are inside gamma. So suppose these points are inside gamma. Then, to calculate the integral, we have the residue theorem. So in this case, with all of these assumptions, the integral of f is going to be equal to 2 pi I times the sum of all the residues. So the residue of f at z sub, let's say z sub j, as j goes from 1 to n. So if you can understand the function f at these points where the function's not holomorphic, and if you can compute the residue of f at these points, then you can compute the integral. And so what this tells you, you can think of this as good news or bad news. The good news is that calculating integrals is now going to be as easy as finding residues. Or you could think about this. The bad news is that finding residues is just as hard as computing integrals. And so we'll talk about some examples here. Now, one connection I want to make here is with the Cauchy integral formula. So I want to talk about how these two thoughts are related here, but the Cauchy integral formula. And so the Cauchy integral formula, just as a reminder, says that, I'm not going to write it down because you've seen this. This is chapter 4 now. So this is material from chapter 4. The residue theorem is chapter 9. This is old news. But the Cauchy integral formula says the following. So suppose you have a function f that's holomorphic, and what you want to do is you want to integrate f of z over z minus z naught, where gamma is some curve that's in G and f is holomorphic over this region G. Okay, so the holomorphicity is over this region G. Then this integral is going to turn out to be equal to 2 pi I f of z naught. Here again, F has to be holomorphic, gamma has to be closed, piecewise smooth, positively oriented, and simple. And if that's the case, you get this nice formula called the Koshi integral formula, that this integral is equal to 2 pi I f of z naught. And so what I want to do is I want to think about how do you compute the residue of this function, f of z over f of z divided by z minus z naught, at z naught. So I want to think about what's the residue of f over z minus z naught at z naught. And so what we can do is we can just kind of immediately apply what we know about the definition. And so f of z being holomorphic, if it's analytic, that means that you have a power series. So this is stuff that we've talked about now in chapter 8. Holomorphic means that you can write it as a power series. And if you write it as a power series, there's a few different ways that you can write it, but you can write it as a power series like this. So c sub k, z minus z naught to the k, as k goes from 0 to infinity. Or you can write it using Taylor's formula, that this is the kth derivative at z naught over k factorial times z minus z naught to the k. So Taylor's formula is basically just the assertion that these coefficients c sub k have this nice formula, right? C sub k is the usual formula that we get from Taylor series. And what we need to do is we need to think about not just this function, but let's actually look at, let me actually wall this off so that this is not exactly part of the problem, but let's look at f of z over z naught, over z minus z naught, I mean. This is going to be the sum from 0 to infinity. Let's just work with the c sub k version, but this is c sub k, z minus z naught to the k minus 1. And so if you write out what this is going to be c0 over z minus z naught plus c1 plus c2 times z minus z naught plus c3 times z minus z naught squared, and so on. Okay, and so that's the formula that we're going to have there. And let's think about what's the residue. Well, the residue is going to be the coefficient that we get for the -1 power. So z minus z naught to the -1. And that's exactly this. This is that c0. And so this is going to be c0, or in terms of Taylor's formula, we know c0 is the 0th derivative, meaning the function f itself, at z naught divided by 0 factorial. 0 factorial is 1. And so it turns out that the residue here is just f of z naught, and that's where Cauchy's integral formula comes from. And you can adapt this if you want to think about how does this work if you were to change the z minus z naught in the denominator to a z minus z naught squared. Well, what would change here would be the coefficient over here, and you would end up with a different exponent. So we'll go into a little bit more about that soon, but that's how all of these integral formulas relate to the residue theorem. The residue theorem is actually stronger than the Cauchy integral formula in its generalizations. Okay, so that's the relationship between the two. So next what we're going to do is we're going to look at some examples. We've seen how important finding residues is for integrating. So next we'll go and talk about some examples for computing residues.